So we now have a nice formula that gives us the number of juggling patterns with a given period and a given number of balls. But in some sense, it feels like we don't quite have it nailed down yet, because we really are looking for the patterns and not the descriptions. In some sense, what we've counted are the descriptions. And you can see that some patterns are described in multiple ways. Let's look at the shower. If we look at the shower with 3 balls, it looks something like this. Now this can be described in 2 different ways, either as 5-1 or as 1-5. But they're both the same pattern. So why should we count it twice? On the other hand, you have patterns such as this, the 3-ball cascade. Now you could describe this as 3-3, 3-3-3, 3-3-3-3-3, any number of 3s, but somehow that doesn't feel right, because you say, look, it's really just should be 3. There's something about the period. And so what are we after? Our goal is to say, now that we have a way to count the number of descriptions of juggling patterns, we really want to say, all right, let's get down to how many juggling patterns are there where we are going to somehow remove these cyclic shifts. In other words, 1-5 is the same as 5-1. And the other thing we'll do is say, look, let's remove anything that sort of has repetition in it. The 3-3-3. Well, look, no, let's make that just 3. So that's our goal for today. So we have this nice question, and where do we start? Well, let's look at a really simple example just to sort of get our mind in the right place. Suppose we look at n equals 3, b equals 3. So how many patterns are there? According to the formula, it's a very easy thing, right? Take number of balls plus 1 to the period, so that would be 4 to the n, and subtract 3 to the n. Well, n is 3, so 4 to the 3 minus 3 to the 3. All right, well, that's 64 minus 27, which is 37. Great. And we actually have them all listed here. So there's 37 patterns, or more precisely, remember, 37 descriptions of patterns. But we see that they oftentimes naturally group together. And many of them are more or less the same thing, just described in different ways. And we've already grouped them in rows. You can see, for example, here, we'll just pick one row out. This pattern 3-1-5 is the same as 1-5-3, is the same as 5-3-1. It's just having a slightly offset beat. But if you were walking by a juggler, you'd never know where they start in terms of their beats. And so, for all intents and purposes, they're the same. Now, in some sense, you say, okay, well, that's very easy to control the offset, because if I have a pattern of period n, I can shift around n different ways. So I'll just divide by the period. So, okay, divide by 3 in this case. And what do we get? Well, we know there's 37 patterns. Divide that by 3, we get 12 1/3. What? A third of a pattern? How can you have a third of a pattern? Well, you can't, because there's another subtlety coming in. And that's this last one at the very bottom, 3-3-3. It's showing up. Now, this is a very valid description of a pattern, and nothing is wrong with it. But in some sense, it doesn't feel right, because the period seems to be kind of misclassified. See, right now it says repeat every 3 beats. We say, look, no, it really should repeat every 1 beat. See, it's a 1-beat pattern repeated 3 times instead of a 3-beat pattern. And so when we are counting, well, we don't want to count this one. That should only be counted when we're looking at period 1 patterns. Okay, so what's going to be our approach? Well, what we could do is say, look, let's identify the patterns that really have a shorter period. In other words, it's a pattern which is repeated several times in the same period. All right, and so once we've identified these sort of suspect patterns, what we'll do is we'll just take them out of our pool, so that all the patterns that remain really have the smallest possible period as n. And now we say, perfect. Since the smallest possible period is n, we can divide by n. All right, done. So this step 2, really easy. Not a lot of work to do. step one, yeah, it's going to take a little bit, but that's okay. That's what we're here to do, is to figure out how to do that little bit. So to get us started, we're going to talk about a sort of a process, an idea, and we're going to build up to what we do. We will come back at the very end and give a nice, complete formula. It does, in some sense, get a little bit messy, but it sort of says, okay, this is precise. This is exactly what we want to count. So we're going to be talking about a process called inclusion-exclusion. Now, you can kind of guess what's going on here, because you see that like the include, that sounds like include, exclude sounds like exclude. So it's like we want to put things in, we want to get things out. And that's what we're going to do. Our goal here is to be counting by sort of saying, okay, what's in and what's out? Because as you know, at one point you might be in, and the next you're out. Okay, let's do a very, very simple example. So suppose you're in a class and there's 45 students. 29 of them like apples, 25 of them like oranges, and 17 of them like apples and oranges. Now, how many students like neither? Okay, so, well, what can we do? Well, we know how many people there are, right? There's 45. Well, we just can say, what? A first guess would say, well, let's take 25 plus 29, add that together, and subtract that from 45, right? That seems pretty reasonable. So we'll take our 45 students, that's all of them, and we'll take out the people who like apples, and we'll take out the people who like oranges. And lo and behold, what happens? Well, we come to the conclusion that, well, let's see, what is this? Minus 29 minus 25, that's like minus 54. And 45 minus 54 is negative 9. So we say, aha, negative 9 people like neither. And then we're like, wait a second, we can't have negative numbers of people. People are things that we can count. We can't have a negative quantity. Something's wrong. All right, well, what's wrong? When I took out the people who like apples and I took out the people who liked oranges, what was wrong is I took out the people who like both of them twice. So I was like, uh-oh, gotta be careful here. I sort of took out too many. So I have to correct. So how to correct? Well, what we can do is we can say, okay, that's not right. What we'll do instead, very similar, say, well, we'll just do a little correction. So same start, take 45 students, take out the people who like apples, take out the people who like oranges, and then realize, okay, so far we're good except for the people who like both. At that point, we've taken them out too often. So we need to correct. So what do? Well, we add in the people who like both to help us fix our sort of overzealousness in taking people out. And now, if we do that, well, we get 8. And 8 is indeed the right answer. Okay, well, that's not so unreasonable. And that's great. We can do these kinds of things, right? Well, I mean, sure, if it's 2 settings, apples, oranges, but you can imagine apples, oranges, cherries, pears, all kinds of fruit. You can make a whole fruit salad. And, well, what happens is things start getting more and more interesting. Because, of course, with juggling, things always get more and more interesting. Well, we need to figure that out. And so to begin down that road, we need to take some time to talk about sets. Now, the basic idea of sets is pretty straightforward. What is a set? Well, what you have are some objects. And then you say, well, a set is just a collection of the objects. And that's it. That's, at the end of the day, that's what we mean when we talk about sets, are collections of objects. And of course, we can have a large number of objects, and then we can collect them in several different sets, and some objects are allowed to be in multiple different sets. Perfectly fine. So that's wonderful. Now, a little bit of subtlety, of course, is keeping track of everything. And we want to have a nice notation. Notation is really important in mathematics. Oftentimes we think, okay, the really important things must be the theorems, but there's also the important things are notation and definitions, because those are the language of mathematics, how we communicate. Good notation, good definitions can really help us understand things much, much better. So it's nice to appreciate definitions, and it's also good to take time just to make sure we understand what we mean and what everything represents. Oftentimes in some classes, there's so many details, you get lost in the language. So let's make sure we all agree on what's going on. So a set, we'll just say, is a collection of objects, and the objects can be anything that we want. Now, when we talk about sets, we don't really care anything about order. We're just saying, oh, we're just putting things together. We're going to talk about our universe, which is the space of all the objects. So in other words, we take all the objects that might be considered, not any object that's possible, but just any object that we might be considering, and we say, okay, that's our universe. We usually use a capital X to denote that. And then we have some ideas. So one idea is union. And so the idea of union is to put things together. So what is that? Well, it says, hey, if I want to put two sets together, I can think of this A union B. And this is everything that's in either A or B. In other words, just sort of putting the two of them together and say, okay, let's make a bigger set. Let's become a larger group. Another idea is to talk about intersection. And that is going to make things a little bit smaller. It says, look, A intersect B, that's how we would read it. What is that? Well, it's the things which are both in A and in B. So in other words, they're common elements. We can talk about a complement of a set. Well, what is that? Well, it's everything not in A. All right, so in other words, you have your whole space of things. You say, look, what's not in this set? Well, everything else. And that's what the complement is. All right, so we're almost there. We can take intersections and unions of one set, but we can also take them of multiple sets. So the intersection of many sets, A1 up through AK, that's the objects in all of them. And the union of sets, it's the objects which are in at least one of them. See, when we take union, it doesn't have to be in all of them, it just has to be in one of them. Okay. The last bit of notation is the magnitude, or the size. So we use these bars. Now you might notice it looks a little bit like absolute value. It's not so bad to think of things in that way. See, what is absolute value about? Absolute value is about measuring size and usually distance. And so, for example, normally when you talk about absolute values, you say, oh, how far am I from 0? That's what it is. So whenever we have things where we say, oh, there's a distance or there's a size involved, it's a good thing to use. Well, let's use the absolute value sign. Okay, so the absolute value of A, it's how many things are in A. I will say set theory can be very interesting as soon as you start getting into infinite sets, so things with infinitely many things, and you can reach some very curious paradoxes. The good news is everything we're talking about is finite, and so it's pretty intuitive most of the time. One of the ways that people often think about sets is in terms of Venn diagrams. And this is a case where it's probably easier to draw a picture than it is to write anything down, a definition. So here, we'll do a very simple case and say, suppose I have this box, and this has everything. So in other words, here's my whole universe, X. And now, a set, it's a collection of objects. So I can have, for example, here's a set A, and here's a set B. And then we look at all the possibilities. There are things which can be outside of both A and B, only in A, only in B, or in A and B, that little part where they intersect. So this overlap is a kind of an interesting sliver here. So this part right there, that's their intersection, A intersect B. Okay. Well, now what can we do? Let's go back to our little formula where we were trying to count. What were we counting? Remember, we had a problem involving apples, oranges, and, well, but what did we say? Well, the idea was say, okay, let's take everybody. All right, so that was all the things, so the whole space. So that's take everybody. Take out the people who liked apples. Let's say A is people who liked apples. And then take out the people who like oranges. All right, that was take out B. And then we said, we have to correct our mistake. And so we added back because we over counted A intersect B. All right, and so that was our approach. And this works for any pair of sets. If I want to know how many things are outside both A and B, then that would be the answer. So in essence, what this is finding is it's finding this part right here, things which are neither in A or in B. So we can write that in the following way. We can say, well, look, that is things that are in A or B would be A union B. And if I want things that are outside of it, I take the complement, and there we go. So that's how we can find the complement of this set. It's in terms of very simple formula. Well, okay, 2 is not so bad. How about 3? All right, well, let's try it. Let's try it. Let's see if we can figure that out. So let's think about what's happening here. So I'm going to have 3 sets, and here we go. A, B, and C. All right, so suppose we wanted to count the same thing. And so to be explicit here, what is it we're trying to count is I want to count everything that's sort of outside of this. All right, well, great. Where to begin? Well, oftentimes a great way to approach a problem is to say, well, let's just get an estimate, right? Let's try something, and then let's start correcting. It's a wonderful way to approach problem solving, is to say, okay, well, it's not the right answer, but it gets us closer to the answer. All right, and now let me fix it a little bit. Okay, that's even closer, and let me fix it. And hopefully, and it doesn't always work, but oftentimes, if you're very careful, what happens is you're sort of like honing in on just the right answer. So where can we start? Well, we can say, well, look, let's just take everything. Okay, great. And so if we take everything, we would have just the size of x. Okay? Now that's obviously wrong. Well, why is it wrong? Well, right now, let's see how all the parts are being counted. So we can think of these as being little individual pieces. And how often do we count each little piece? Well, everything so far is being added in once. Okay, great. Now the problem is we do get the parts that we want, but we're now getting parts that we don't want. Okay, time for some correction. So how can we correct? Well, generally speaking, it's better to start working with the bigger pieces and going to the small than going from the small pieces to the big. Well, why is that? I mean, it sounds obvious, but why is it? Well, the idea here is that if you have a large piece, of course, it influences many, many things, and so it's hard to keep everything in check, whereas small pieces influence only very small things, and you say, okay, so that's easier to control. So that's why we really want to start with the large things first, where we're like, okay, that's great, just throw that in, and then refine with the smaller and smaller as we go. All right, so what's something slightly smaller than everything that we can talk about? And remember, what can we talk about? Well, we can talk about the sets A, B, C, and ways to put them together. Well, so the next thing down would be if we looked at the sets themselves, the A, B, and C. All right, so let's see what's happening. So what's happening is we're overcounting. So let's simply take out A, take out the B, and take out C. All right. Now, great news is that'll help fix our count. Well, let's see where we stand. Now, notice everything on the outside is not affected when we take these out. Here, parts that are an A, well now, that's going to be only counted 0 times because it was counted once and then you took it away. Similarly, in here and in there. So, because we took it away. But let's come into some of these smaller pieces. Let's start here. This part is in both A and B. Now notice what happened is we put it in once, took it away once, took it away a second time. So what does that mean? Where are we at? Well, it means that we are at a net of -1. And so we went too far. Well, that can happen. And so the same basic count says, all right, great. How about that little piece? Okay, now, where's the contribution? Well, for this little piece, that's the one in A, B, and C. So all three simultaneously. We counted it because it was part of everything. And then we took it out once, twice, 3 times. So now our net count is -2. All right. Well, progress of sorts, right? See, we got this part 1. That's good. We like that. And we got these as zeros. That's good. But now we're like, uh-oh. As an end result, we see what happened. We started with everything, and now we took away too much. And we say, oh, that's bad. Okay, so now we've got to correct, just like what we did up here. So how are we going to do that? Well, no surprise. We say, okay, let's go to our next smaller things. What would be next? Well, what we can do is look at things which are in 2 sets at the same time. So, for instance, we can look at, say, things in A and B. And let's just focus on things in A and B. So this little piece here, we say, oh, right now it's -1. So, to get the right count, I want to get to 0. I never want to include it. So, we will add in A and B. And we'll do it for the same things, right? A and C, B and C. So, add in A and C, add in B and C. So, let's update our counts. The only things that are going to be affected are the things which are in at least 2. So, just these little pieces in the middle. So let's suppose we start here. Something that's in both A and B, but not this middle part, so not in C. So what happens? How often does it get counted here? Well, once, plus, once minus, and once is a plus. So the net effect, 1 minus 1 minus 1 plus 1, is 0. Aha! Good. That's great, because we don't want to include it. And so these are all zeros. All right, beautiful. How about the one in the middle? This little sliver here. Okay, so where does it show up? Well, it shows up once, all right, a plus, minus, 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 plus, plus, plus. What's our net count? Well, 1 minus 3 plus 3. So our net count is now at 1. And now we're like, wow, we're doing great. We're really improving our count. And we say, hey, look, the one on the outside is good. All these zeros are good. There's just this one little piece in the middle that's off. So we just have to correct that little piece. That little piece is inside of everything. So to correct, what do? Well, we subtract it. So now subtract. A intersect B intersect C. And that will take care of that. So now that's counted 0 times. It's really sorry, hard to read there. But the important thing is, now no matter where you point, if you're outside of A, B, C, the net count, how many times did you count it in this collection, is 1. And if you're anywhere inside of here, the net time that you count is 0. Now, there is something that we should pause, because it's going to help us sort of understand what happens next. Because we're going to take a little detour. We say, okay, so far we can do this with 2 sets. We have a little formula. We've now been able to do it with 3 sets. And in particular, what do we mean we've done it? Well, in particular, we have found a way to write this A union B union C complement and see how many things are in there. We want to do this very generally. And so we want to say, well, what is actually happening? What's making it work? And how can we figure out what's going on? And to help us sort of spot that, I think it's useful to think about what's happening in a few different places. So suppose I take a point here. So in other words, I'm outside of A, B, and C completely. So right there. How many times do I get counted? In other words, what's the contribution? Well, the answer is once, right? That's it. Now, suppose I move into one of the sets, but I'm only in one, just one set. Well, how many times do I get counted here? Well, you get counted once for the whole space, and then you get counted minus for that one set. So it's once and then minus 1. And, well, okay, what if I'm in 2 sets? So say like right there. All right, if I'm in 2 sets, how often do I get counted? Well, once, okay, and then because I'm in 2 sets, I'll show up in 2 of these, so minus 2. And if I'm in 2 sets, I'll show up in one of these. So for example, this one right here shows up in that B intersect C, which is minus 1. What if I'm in 3? So I'm in this part right here. Well, I'll show up once in everything. I'll show up in each one of these individuals. So there's 3 of those possibilities. I show up in each one of these. So there's 3 of those as well. And I'll show up in that one. And there's 1 of those with the right sign. And what's the key? Well, the key here, as you'll notice, we get 1 in just the first case, just when I'm on the outside, and everything else is 0. All right, great, no surprise. Do you notice these numbers? They're not just random numbers. They're kind of famous. Have you seen this pattern before? Don't worry about the plus minus. Look at the numbers. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Does it sound familiar? Yeah. It sounds a lot like binomial coefficients because it's binomial coefficients. So we need to take a short detour and make an observation. So we were looking at sort of adding up binomial coefficients where we add along the rows, but instead of saying plus, 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 no, that's not interesting. Plus, minus, plus, minus, plus, minus. So we're going to look at this alternating sum of binomial coefficients. So that's what you see here. So this is the sum. That's what of course, sigma always represents. So we're adding up. Alternating means you change sign. Plus, minus, plus, minus. So that's what this minus 1 to the k does. And then this n choose k just means you're using the binomial coefficients down on the nth row. Now, we can actually compute some of these. And so, for example, with 1, well, nothing to do there. It's just 1. 1 minus 1, well, 0. 1 plus 2, sorry, 1, not plus, minus 2 plus 1, 0. 1 minus 3 plus 3, minus 1, 0. And 1 minus 4 plus 6 minus 4 plus 1 is what? Well, minus 4 makes minus 8, and 1, 6, 1 makes plus 8, and so you get 0. Okay, 1 minus 5 plus 10 minus 10 plus 5 minus 1, we get 0. All right, I think we can kind of spot there's this nice pattern going on here. And so what's the answer? Well, it turns out there's two possibilities. If we're in the very first row, which we would call the 0th row, then what do we have? Well, we get 1. So this is 1 if n equals 0. And then otherwise, we get 0. That, at least, seems to be the pattern. We have to be careful here, because we can't just say, oh, it seems to be the pattern, and therefore it is the pattern. That's not how math works. What we can do is we say, ah, this seems to be the pattern. Now, let's verify it. So, what can we do? Well, you might say, hey, some things are really easy, right? So, for example, 1, 3, 3, 1, you see there's sort of that symmetry which comes into play. And so, like, okay, maybe that will explain it. And you can actually use it to explain certain rows. But you can't do that for something like 1, 4, 6, 4, 1, because what is that? You know, there's not that symmetry that goes on. You know, here, where there was a -3, there was a +3 right across from it. You can see it here, down here as well. 10, -10, -5, +5, 1, -1. So how can we actually verify this in general? Well, there's another way to think about what's happening here. If, first off, we'll say the fact that it's true for n equals 0 is great. So let's assume n is at least 1. Well, what's happening here is when we alternate, we want to say something equals 0, so we have a lot of stuff being added and a lot of stuff being subtracted. So what's the stuff being added? Well, we're adding it whenever k is even. We're subtracting whenever k is odd. So what we can say is this is the same as for n greater than or equal to 1, the sum of the k which is even of n choose k, it has to be the sum where k is odd of n choose k. That's the same claim. Do you see how it works? Right? -1 to the k, we add, subtract, and group things by the signs, which means we group things by parity, even or odd. Okay, so why is this true? And another way we can think about it is what? Well, really, on the left-hand side, here we have the sort of groups of even size, and on the right-hand side, what do we have? Well, we have groups of odd size. All right, well, that's good. So how can we show that there's the same number of each? Well, what we'll do is we'll do a pairing. And we know that there's at least one element. How do we know that? Well, because we said it. That's a good reason to know it. So we know there's at least one element, and we say, okay, we're going to have a special element. We're going to tie a bow to that one element. And we're going to say, all right, now what we'll do is for every set, either that special element is in it or it's not. If it's in it, what we'll do is we'll say, look, you should pair with the same set where we take that special element out. And if it's not in, we say you should pair with the same set where we put that special element in. So in other words, we pair things up. Now, what's the important thing? Well, the important thing is that as we pair, we do it in such a way that the size of what we pair is off by 1. So if one of them is even, the other one is odd. And you'll see everything got paired, and therefore, what's our conclusion? Well, the conclusion becomes the following. It says, hey, I compare all the sets with an odd number with all the sets with an even number in this one-to-one fashion, and therefore there must be the same number of each. And we're done. That's it. That's it. Okay, so now we have our alternating sum of binomial coefficients. By the way, this is a combinatorial type argument, and you might say, couldn't we do something a little bit simpler, which is to say, let's use the binomial theorem. Okay, yeah, let's do a binomial theorem proof. What's the binomial theorem proof? Well, the binomial theorem proof is the following. We'll just make a side note. You know, it's always nice to do things in different ways. It's fun to see different proofs. And what we'll say is, look, here's another way to think about this sum. It's sum over all k, n choose k, minus 1 to the k, and 1 to the power n minus k. And now we say, oh, what's going on? Well, this is the binomial theorem, which says that this is equal to something to the nth power, and namely minus 1 plus 1. And it turns out minus 1 plus 1 is 0 to the nth power, which is 0 as long as n is at least 1. Now, what is 0 to the 0? Well, you just have to say, let me pick a convention. But for now, that's another way to see it. Now we have two proofs. It must be twice as true. Very true. Highly true. Okay, good. Well, so how do we use this? Okay, let's turn and look at the general formula. So this is the general formula. And if you see it, you kind of like, there's a lot of notation going on. So let's talk about what we are actually doing here. So our goal is we're going to count everything that's in none of the sets. So we have a collection of sets, A1 up through AN. We say, okay, I want to know everything that's not in them. How many are outside of all the sets? All right, well, the same as asking that question is to say, take their union and take the complement. That's the things that are outside, and what's the size of it? All right, so that's our question. And we say it is, of course that's what an equal sign is the word is. You take all the objects, and then you're going to start taking things out, putting things in, out and in, out and in. That's the inclusion-exclusion. Sort of, you're going to start doing some correction, and at the very end, everything works out. Now, here's where the notation can either get away from you, or you can relax a little bit. Don't stress too much about this notation. We just want to do the ideas. So what we're going to do is we're going to add up, and we have this fancy I. Think of I as being your indices. And but what are we really talking about with I? What we're really talking about is we're going to say, let's look at all possible groups of these sets. It's like we're taking a set of sets. And yes, you can do things like sets of sets. And so whenever we talk about I, what we're really talking about is we're picking out some number of sets. And we're going to do it in all possible ways. And here, you'll notice it says, hey, don't take an empty set, which means you always have to take at least something. And now, so suppose we've taken some sets. So maybe we've picked A2, A5, and A11. All right, so we have 3 sets. So we say, all right, you're going to count how many sets you've picked, which is 3, and that will determine whether you add and subtract. So you take -1 to the number of sets. And then this says, just take the intersection of the sets that you've picked. So what's in A2, A5, and A11 simultaneously. And that's what if you do that all possible ways, then it all works out. All right. Well, let's try to understand this a bit. And how does this work? Well, there's a couple of cases. And so suppose, for a second, something here is only in X. So not in any of the sets. All right? Only in X. Well, how many times does it get counted? The answer is it only gets counted in X, because it's not in any of those. So the right-hand side will equal 1. Now, great. No problems, we say. No problems. Okay, so now suppose we're in M of these sets A1 up to AN. Okay? Now, how many times will we be counted on this right-hand side? Well, the answer is we're going to be counted here once. All right. And now we start saying, well, I look at all the possible ways I can pick out sets where it would show up. Well, it would show up in M times of the sets. So I'm trying to make this more complicated than it should be. So in terms of just individual sets of group of sizes 1, it shows up in n of them. So we're going to subtract m choose 1. So this is like, just A1, just the first set it's in, just the second set it's in, all the way up through just the mth set it's in. But now it's also going to be counted when we look at intersections of pairs of sets. So in that case, because there's pairs, 2 sets, well, that'll be showing up as m choose 2, because there's m choose 2 ways because we have m sets. So we're going to pick 2 of them, and then that's going to show up. And now we say, okay, but it'll also show up in sets of groupings of 3. All right, and that's going to be as a minus, and then so forth and so on. And so what happens is that in the right-hand side, in the counting, it all becomes this alternating sum of binomial coefficients. So our final count, all the way up to the last thing, whether it's plus or minus depends on parity, and that is 0. All right. So that's the idea. That's the philosophy. All right. So with this case out of the way, and I don't want to delve too much deeper into it, if this is confusing you, just go back to where we did the Venn diagrams and look at the case for 3. It's much easier to just sort of work your way through a single case and say, okay, what's actually going on? And then say, okay, what's the right notation? At the end of the day, it's all about counting how many times each thing contributes. What's the net contribution? And it should either be 1 or 0. If it's not, okay, something is wrong. There has to be a fix. So we're going to go to something which is going to feel really different, but don't worry, it does connect, I promise. There's something going on. So now we're going to talk about the Mobius function. Well, what is the Mobius function? It's a function where you plug in a whole number, and the output is either 0, 1, or -1. And the rule is very simple. It says, all right, if you have any prime that when you square it, it divides in 0. That's the answer. On the other hand, if all your primes are never squared in terms of your prime factorization, then what you do is you count how many primes there are, and you say, okay, it's -1 to that number of primes. So if you have an even number of primes that divide, that's going to be a positive. If you have an odd number of primes that divide, that'll be a negative. Okay, so that's the function. Let's try some examples, because it's good to practice. And we should note, for 1, what do we get? Well, there's no primes that divide, 0 primes. So -1 to the 0 is 1. Okay, how about for 2? Well, just 1 prime, so that's -1. 3, just 1 prime, that's -1. 4, well, notice 4 is 2 squared. Well, that means that we're in the case where there's some square prime dividing it, and so we get 0. All right, how about 5? Well, it's prime. It turns out there's a lot of primes in the small numbers. They get more sparse as we go on. How about for 6? Well, what do we have? Now there are 2 primes, 2 and 3. It's there's no square that divides it. All right, so 2 primes, that would mean even number, that's a +1. How about 7? Well, that's a single prime, -1, 8. Well, 4 divides it, so we're back to 0 again. How about for 9? Well, 3 squared, so that's 0. All right, are we convinced? Well, how about, let's try some bigger numbers. 24. All right, well, okay, that's 4 divides that, 2 squared. All right, it's out, 0. How about, say, 30? What would that be? Well, what divides 30? 30 is 2 times 3 times 5. No squares, that's good. There's 3 different primes, so that would make it a minus. And again, you can do this with any number that you want. There's a nice formula. And so we can plug in our favorite number. No, that's not 100, but you know, these are fairly straightforward to compute. All right, well, great. That feels like it doesn't have anything to do with what we just talked about. But it turns out that there's this really interesting and beautiful idea that involves the Mobius function that at its core is really behaving like the inclusion-exclusion argument we talked about. And so if we can get some sort of intuition that says, hey, inclusion-exclusion works, then this next step will be like, oh, okay, this should also be working as well. So what's that? Well, so we want to talk about Mobius inversion. And it's a really interesting idea. It says, suppose we have some functions which are related. So in particular, I have a function f, and I can create a new function g in the following way. Namely, if I want to say what's the value at g at any particular n, I look at all the divisors of n. So this is our notation, something which divides into n. So I'll take all the divisors of n and look at what's the function at that divisor for f and add all those up. So given a g, it's as a sum of f. So great, I have g in terms of f. Mobius inversion says, hey, I'd like to turn this around. I'd like to figure out what is f in terms of g. All right, so can we do it? It seems like it should be possible. And the answer is yes. In fact, it's a very beautiful, elegant answer. And so the function f is defined as take all the divisors of n. And now we have that Mobius function, which is why we talked about it, because it was needed, of that divisor times the function g at n over d. So that's the formula, right? Okay, there we go. Let's try a specific example. You know, it's good to look at our examples. So suppose we pick a number. Let's suppose we pick, say, n equals 12. We can do that. And what do we have? Well, according to this, it says, hey, if I want to know what f of 12 is, what can we do? Well, we look at all the divisors of 12. Now there's 1, 2, 3, 4, 6, 12. That's a lot of divisors. But all right, let's work through it. Now, because of the Mobius function, we can actually save ourselves some work. Okay, which divisors do we care about? Well, we only care about the ones which are square free, which means I don't want anything with the 4 in it. So we have 1. That's a nice square free divisor. So mu of 1, and that would be g of 12 over 1, which is g of 12. We have 2, mu of 2. That would be g of 6. We have 3, mu of 3, g of 4. We can do 4. We're not going to look at because mu of 4 is 0. Out. We can look at 6. That doesn't have any squares. So mu of 6, g of 2. And 12, we don't look at because that has 4 divides 12. 4 is the square of a prime. All right, so that's the claim. Well, let's actually verify this. Now, a couple things we should do is, of course, note what's going on. So the Mobius function, when we talk about things which are plus or minus, we really mean there's a sign. So it's a plus, minus, minus, plus. So let's go through and work through what each one of these contributes. So we'll start with, say, g of 12. Well, g of 12, and that's being added. Well, what are all the divisors of 12? Well, there's 1. Whoops. I'm now coming up to here. G of 12 would be f of 1. There's 2. There's 3. There's 4. There's 6. And there's 12. All right, how about g of 6? Well, remember that's being subtracted. That's going to be all of the things which divide 6. So, for example, 1 divides 6, 2 divides 6, 3 divides 6, and, of course, no surprise, 6 divides into 6. All right, whoop, I don't need another equals. Now, the next one, g of 4, everything that divides 4. Well, that's what? 1 divides 4, 2 divides 4, and 4 divides 4. And finally, our g of 2, that's being added. And what's that? Well, that's everything that divides into 2. Well, that's 1 and 2. And now we take a look. And we say, all right, what's going on here? What's going on? Well, let's start with our f of 12. How many times does it show up? Well, it shows up exactly 1 time. So namely, it showed up right here at the very start, where we had mu of 1, g of 12. We had a single f of 12, and there we go. That's good. Now, what should happen is everything else should cancel out. So that's what we're hoping for. So cross our fingers, everything else cancels out. And let's see. You know, we shouldn't just hope for things. They should actually be true. So proceeding, we look and say, okay, well, we have an f of 6 and a minus f of 6. Aha! They do cancel. Gone. And for f of 4, you have an f of 4 and minus f of 4. Gone. For f of 3 minus f of 3. Gone. Good. And notice the pattern. Plus 1, minus 1. Plus 1, minus 1, plus 1, minus 1. All right, how about for f of 2? Plus 1, minus 1, minus 1, plus 1. Gone. And same for f of 1. Plus 1, minus 1, minus 1, plus 1. Gone. Good. Now, the pattern. Really, it's 1, 2, 1. Plus 1, minus 2, plus 1. Plus 1, minus 2, plus 1. That same pattern is what we were talking about with inclusion-exclusion. It's the same reason why Mobius inversion works. So what's going on here? Why does this all work out in the end? Well, so here's sort of the idea. When we're looking at all the sum, we say, well, look, f of n only shows up in one place. And where does it show up? Well, it shows up when we look at, namely, that mu of 1 g of n. That's the only place it shows up. And so sort of a net contribution is plus 1. Okay, but what if I'm not f of n? What I want to show is what's the net contribution? Well, it should be 0 if what I claim is what's actually true. Okay, so if I look at any other number that divides into m, so suppose m divides into n, and in general, when I look at this n over m, it has, well, let's say k distinct primes. Now, I'm not counting multiplicity here when I talk about k distinct primes. So I'm saying, how much do they differ? How many primes? Are there, like, suppose it was, say, 24. So n over m was 24. Well, then the primes involved are 2 and 3. I don't care the fact that 2 shows up multiple times. I just want to say it's 2 or 3. And here, this is our great, okay, so why is this nice? Well, you see, what's happening here is when we look at this Mobius function, remember, it only cares about things which are square free. So we only have things which are products of distinct primes that do a contribution. So that's why I don't care about, is it, 8 instead of 2. No. I just care about the 2-ness of it. I want it to be very 2-y. So what happens, what's the contribution? Well, suppose we have our primes P1, P2, and PK. So those are our primes. Well, then what we'll look at is the following. Well, we would have mu of P1, g of n over P1, and all the way up to mu of pk, g of n over pk. And notice, this would definitely be included, this m is going to show up in all of these. All right, then we go and say, okay, how about 2 primes, p1, p2? Well, g of n over p1, p2, and all the way through product of 2 primes. Okay, and then you say, okay, how about p1, p2, p3? G of n over p1, p2, p3. And look at all of those, so forth and so on. And the key here is whenever I look at g of n over a product of some collection of these primes, so it could be 1, 2, all of them, none of them, and of course it could be none of them, right? Mu of 1, g of just n. In each one of these, that's the one, I shouldn't say one place, these are the only places where m is showing up. In other words, the f of m gets counted. Now, what is the contribution? See, what's our net count going to be? Well, at the very beginning, we get a plus 1 from this g of n times mu of 1. Now, if we have a single prime, when we look at those, well, each time that mu is going to be a minus, so we're going to subtract, and it shows up in all of these. Well, we had k primes, so really we're going to subtract k choose 1 because we're picking one of the primes. Say, okay, how about the next line where we have 2 primes differ? Okay, well, we pick the 2 primes, k choose 2, in all possible ways. Great. And their contribution, because of the Mobius function, is positive. And we keep going, right? When we go down to 3, it's so forth and so on, minus k choose 3. And what we get is this alternating sum of binomial coefficients, which is 0. And so our great aha is our net 0. So we say, perfect. That is exactly what we want to happen. So by the same logic, and I haven't done the best presentation. This is a time when animation would be great, but unfortunately we work with what we can. But what's happening is that the Mobius function, it's the same sort of adding, subtracting, just sort of everything balances out just right. And it boils down to a very simple, elegant idea. The alternating sum of binomial coefficients is 0. And so, wonderful. Now, you might think, why would we want this? I mean, yes, it's possible, but should we have? And so the reason that we might want to do this is in some cases we say, it's very easy to find g, but we don't really know what f is. And so that would be a case where we could turn around and say, aha, since I found G, now we have F. And, well, there's at least one scenario that we care about. So for us, it turns out to be wonderful when it comes to counting juggling patterns. So we've written down our rule for this Mobius inversion. Say, okay, great. And now, suppose we think about our juggling patterns. Now, what can we count? So we're going to let G of n be the patterns with B balls in period n. So in other words, it's really the descriptions of the patterns. And we have, that's what we counted. We've counted how many descriptions of patterns there are. Now, what do we want? Well, we really want to say, we want to remove patterns which are kind of built off of smaller patterns repeated. And how can you take a smaller pattern? Well, you take some divisor of n and you copy it. So suppose d divides n, and then you say, okay, take that d and just copy it n over d times, whatever that pattern is, and now you have a pattern of n. We'd like to somehow get rid of those. So what we'll do is we'll look at a function f, which is the patterns with b balls and minimal period n. In other words, it's not built up from a smaller pattern. That's what we're really after, is those sort of like true, proper period n. And so say, okay, what's the case? Well, here's the thing. If I look at all the patterns with b balls in period n, then it must be formed by saying, look, the only way you can find a pattern with period n is either you are period n or you're built off of something which is repeated, but the only way you can repeat something is if you're a divisor of n and you have that pattern. So that's f of d for all d that divides n. So we now turn it around because we know what G is, and so we can get f. So our number of patterns with b balls and smallest period n, so we can't break it down any further. All right, that's what we're after, is our sum, d divides n, the Mobius function of d, and then g of n over d. Well, what is g of n? It's this number of balls plus 1 to the period minus the number of balls to the period. So b plus 1 to the n over d minus b to the n over d. Aha! Success! Now, in some sense, you're like, this looks a lot more complicated than just like, b plus 1 to the n minus b to the n. It is more complicated, but it's also sort of more pure. It's like, okay, this is really capturing the proper number of juggling patterns and not just their descriptions. Well, one last step. This was step 1. Remember, there are 2 steps. You're like, no, what was step 2? It's been so long. Okay, what is step 2? Step 2 was divide, right? Because now we have our period n, and we say, look, I can think about the cyclic shifts. In other words, if I have a description of the pattern, you take that last row and you move it to the front. It's the same pattern, just described in a different way. And you can do that, n times. And so we really say, look, we don't want to count all of them. We just want to count 1. And so divide by n. And now that just adds that 1 extra piece. So here we go. This is probably the best formula. Because what are we counting? It's the number of juggling patterns. We don't count anything that's the same by cyclic shifts. We don't count anything that has really a smaller period built into it. It's the smallest period that's possible for that pattern, and it has b balls. And so it's 1 over n, sum over all the divisors of n, Mobius function of d, and b plus 1 to the n over d minus b to the n over d. All right, well, should we try it? Okay, let's actually do one example. Okay, so suppose, well, let's make it interesting. See, if your period is prime, it's pretty easy to correct. Really easy to correct. So let's try something that's not prime. So let's choose n equals 6 and number of balls equals 3. All right, so what's the rule? According to us, that's 1, 6. We're going to sum over everything that divides 6, Mobius function of 6. And then we're going to have b plus 1. No, not Mobius function of 6, Mobius function of d, sorry. I can read. All right, then we're going to have b is 3, so that would be 4 to the 6 over d minus 3 to the 6 over d. Okay, so everywhere there was an n, we put in 6. Everywhere there was a b, we put in 3. We got to keep going. Well, maybe we don't have to, but we should for science, right? All right, so what does this become? 1/6. Okay, so what are the divisors of 6? Well, 1, 2, 3, 6. So let's start with 1. So we would have the Mobius function at 1, and that would be 4 to the 6 minus 3 to the 6. Okay, so this here, just keeping track. Just for sanity, we'll write underneath. That's d equals 1. And okay, go to 2, and that will be 4 to the 6 over 2 is cubed, and 6 over 2 still cubed. Okay, good. So that's d equals 2 plus, take 3, right? 3 divides 6, and then we're going to have 4. 6 over 3 is 2, so 4 squared minus 3 squared. That's going to be 3. And now finally we take 6. So we're going to have Mobius function at 6. And, well, 6 over 6 is pretty easy. That's 4 to the 1 minus 3 to the 1. All right, good. Now, there we go. And, well, let's keep going. Well, let's put down our signs. We have our pluses and our minuses. So we get a plus, minus, minus, plus. So, all right, what do we have? Well, we should have 1/6. Now, 4 to the 6, which is, right, 4,096, exactly. We all got it together. Okay, well, you might be like, really? Yeah, so this is, the nice thing is 4 to the 6, see, 4 is like 2 squared, so it's really like 2 to the 12th. And it's like powers of 2, we love powers of 2. And so, you know, it's a fun game when you're walking along and like, okay, let me see how high I can go with powers of 2. 1, 2, 4, 8. So anyways, it's 4,096. All right, 3 to the 6, I'm not going to be able to pull that out of my head. I mean, that would be like me saying it was something like 729. It turns out 3 to 6 is 729. Now, how do you get that? Well, one way you can think about it is that it's really like 9 cubed, right? 9 times 9 is 81. 81 times 9 is 729. Okay, so that's the first piece. Okay, subtract. Okay, now we're getting to numbers that are a little bit easier for us to work with. 4 cubed, 64. 3 cubed, 27. Subtract. 4 squared, a lot easier to work with. 16. 3 squared, 9. Add, and 4 minus 3. By the way, do you see what this is? This is 1. It should be a pattern of period 1 that involves 3 balls, which is 3. So this pattern is easy to say what it is. All right, well, it's always dangerous to do arithmetic in front of a live audience, but I'm going to do my best just to say, hey, it can be done. I strongly encourage you to use computers or calculators when you can. So 4 minus 3, that's not so bad. 60 minus 9, 7. 64 minus 27, 37. So what do we have here? 37 and 7 makes 44. And that's being subtracted plus 1. So all of this becomes a net 43 being subtracted. All right, so there's also, of course, this 729. And so we really have 4,096. And then we're going to subtract, well, 729, but we're also going to subtract 43. Now, if you take 729 and 43 and you were to combine them together, you would get 772. Okay, so that's what we need to subtract. And, okay, well, that's 4, 2, and 40 subtract 7 is 33. So, there we go. All right, that seems to be the answer. And so we are up to 1/6 of 3,324. Now, if we've done our work right, what should be true? We should end up with a whole number because we're counting patterns. You know, you can't have a piece of a pattern, you know, because it's either a pattern or it's not a pattern. So after I divide 3,324 by 6, I should have a whole number. If at this point it's not a whole number, that means mistakes were made, which is quite possible, especially when you do things by hand. And if mistakes were made, what do? You go back and you check your work. You don't keep saying, well, all right, whatever. No, check your work. All right, so does 6 divide 3,324? And the answer is, fortunately, yes, it does, which is good news. It means we might have actually gone through this without too much danger. Namely, it's going to be 554. So, and this is not so hard to check. So that says that in terms of if I have 3 balls and period 6, there are 554 distinct patterns. In other words, patterns which look completely different from each other, and none of them are built off of any smaller period. And that's the count. Wow, what a number. Beautiful, beautiful. And yeah, sure there's more work, but it feels better. It feels like this is really what we're after. This is the right kind of count. Good. Done. Done.